From social media data to financial transactions and weblog data, graphs are ubiquitous in today's interconnected world, and the size and scale of graph databases is increasing exponentially with modern applications. To classify and understand relationships in graph databases and drive insightful decisions for business advantage, enterprises are racing to adopt graph AI technologies to gain competitive advantage. Applications of graph AI technologies include understanding diseases and cures based on genetic mutations, identifying fraudulent activities from banking transactions, and extracting insights from social media data. An example is in the area of network security, where breaches at corporations have resulted in billions of dollars of losses and erosion of company reputation. Prevention of these attacks and securing corporate networks from intruders is a business-critical priority for CEOs and CIOs. By storing the underlying network topology in a graph database and applying graph AI technologies, companies are able to stop brute force or denial of service attacks, even when the underlying network patterns, which can be represented as graphs, are changing dynamically. In a major advance to the field of graph AI technologies, FUJITSU Laboratories developed deep tensor technology that uses new tensor processing techniques and a deep neural network to automatically extract relevant features from graph databases. To add a layer of usability and explainability to the core deep tensor technology, FUJITSU Laboratories also developed accessible deep tensor, ADT, which is integrated to leading graph database platforms, including Neo4j. ADT provides powerful modeling and visualization tools to enable a business user to rapidly leverage the core AI technology. And by presenting the data and the rationale for the decisions in an easy-to-understand format, adds explainability and opens the AI black box to external validation. As the size and scale of graph databases grow exponentially, ADT will continue to enable new and innovative applications, and FUJITSU Laboratories will collaborate with solution partners such as Laurus to deliver the power of ADT to our customers.
Hello, everybody. We are back for our third webcast of the day. And most of us that are trying to deliver this experience to you are getting a tremendously valuable lesson in extreme multitasking. Somebody should do a study at some point to just determine how everybody on Earth has improved their multitasking skills after this last year of ubiquitous video in everybody's homes. Without further ado, let's get going. I'd like to, and very privileged to introduce our third keynote of the day. The title of the keynote is How Not to Destroy the World with AI. And I'd like to introduce Dr. Stuart Russell. Dr. Russell received his BA with first-class honors in physics from Oxford University in 1982 and his PhD in computer science from Stanford in 1986. He then joined the faculty of the University of California, Berkeley, where he's a professor of electrical engineering and computer science. He is also an adjunct professor of neurological surgery at UC San Francisco and vice chair of the World Economic Forum's Council on AI and Robotics. His research covers a wide range of topics in artificial intelligence, including machine learning, probabilistic reasoning, knowledge representation, planning, real-time decision-making, multi-target tracking, computer vision, computational physiology, global seismic monitoring, and philosophical foundations. It's my pleasure to welcome Dr. Stuart Russell.
Hi, I'm Stuart Russell, and I'm going to talk to you today about a very boring subject, which is how not to destroy the world with artificial intelligence. So to begin this story, we will start with Alan Turing. He is the founder of computer science and arguably the founder of artificial intelligence. In 1950, he wrote a very famous paper that introduced the Turing test, laid out the basic framework for artificial intelligence and machine learning. What a lot of people don't know is that in 1951, he gave a lecture on the radio in which he said the following: "It seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control." So I'm going to explain why that might happen and how to avoid it. So we fast forward to today, all kinds of exciting developments, self-driving cars on the horizon, the defeat of Lee Sedol, the world champion at the game of Go, and many other really amazing developments in artificial intelligence. So if this continues and we achieve what we might call general purpose or human level artificial intelligence, the benefits are really enormous. For example, we would have essentially everything as a service. So not just software as a service or travel as a service, but everything. We could use that to lift the living standards of everyone on Earth up to a respectable level. So not actually the science fiction ideas of curing diseases or allowing us to live forever or fast and light travel, but just doing what we know how to do already on a global scale at greatly reduced cost. So this would raise GDP by a factor of roughly 10, and the net present value of that will be about $13.5 quadrillion. So that's the value of the prize in very conservative, simple economic terms, the value of the prize that we're aiming for with human-level AI. Another advantage is that because general-purpose AI represents essentially a source of wealth on demand, then there's no reason to be fighting over a finite pie of wealth. It would be like fighting over who has more copies of a digital newspaper. It just wouldn't make any sense at all. So that's the good side. But a consequence of creating human-level AI is that we have created systems that are able to make better real-world decisions than human beings. And this is really what Turing is concerned about, because the ability to make decisions well is intelligence, and it's that intelligence that gives us power over the world. So Turing's question, rephrase, is how do we retain power over entities that are more powerful than us forever? So to explain that question and to answer it, we really need to go back to the beginnings of AI and the fundamental definition of the field and how we think about it. So I call this a standard model of AI. And roughly speaking, it's that we create machinery, optimizing machinery for achieving objectives. And then we exogenously specify objectives for the machines to carry out. For example, you get in a self-driving car. It doesn't have an objective, a destination. You give it one, take me to the airport. It figures out how to do it and carries it out. So this is the standard model for pretty much every kind of AI system and every application of AI. And it's not just AI. It's also control theory with cost functions, statistics with loss functions, operations research with reward functions, and economics with social welfare and utility functions. So I would like to argue that this model, despite its enormous success, is fundamentally flawed, because in the real world, we cannot specify objectives completely and correctly. And if you specify them incompletely or incorrectly, then you have a machine that's pursuing something that is contradictory to what you really want. And that's a problem when the machine is more intelligent than you. This is not a new lesson. We've known this actually for thousands of years. Here's King Midas, who specified that everything he touched should turn to gold, and then his food and his drink and his family turn to gold, and he dies in misery and starvation. We have Goethe's tale of the sorcerer's apprentice, who specifies that the groom should fetch the water for him, but he forgets to specify the amount. And then he has to get the sorcerer to rescue him from drowning. Or if you get 3 wishes from a genie, your third wish is always, please undo the first 2 wishes, because you've made a mess of the universe. So even though those lessons have been known for thousands of years, we keep forgetting them and we keep repeating the same mistakes. So today, with social media, we have learning algorithms that control what billions of people spend most of their days seeing and watching and reading. And those algorithms are designed to maximize some objective. Let's say it's click-through. It could be some more complicated objective. But it's a fixed objective that is given to the algorithm, and then it has to figure out how to maximize that. So you might think, well, an algorithm that's supposed to maximize click-through is going to have to learn what people want. And that seems pretty reasonable. Send people things they're interested in and don't send people things they're not interested in. But actually, that's not what the algorithms do. What they do instead is they learn to modify people to be more predictable. This is just a straightforward consequence of giving an objective to a reinforcement learning or a similar kind of algorithm. It will figure out a sequence of content to send people so that at the end of that sequence, the person has become more predictable, whether they're a violence addict or a neo-fascist or an eco-terrorist. It doesn't really matter to the algorithm. You're just a sequence of clicks to the algorithm. But they can turn you into a sequence of clicks that's more predictable and therefore more profitable. So in this model, the standard model of AI, when you have a misspecified objective, the better the AI system, the worse the outcome. These are very simple algorithms. If they were more sophisticated, if they were more intelligent, they would do a much better job of modifying you to be more predictable. So you would get a worse outcome. The algorithm is better able to achieve the incorrectly specified objective. It's also better able to protect itself against attempts to interfere with achieving that objective. So how did we get into this mess? I think it started back in the 40s and 50s when we were formulating the nature of the field, the goals of AI and cybernetics and control theory. And we had from philosophy and to some extent from economics already the notion of the rational intelligent agent. So in that model, humans are intelligent to the extent that our actions can be expected to achieve our objectives. And so the natural translation to create machine intelligence is to say that machines are intelligent to the extent that their actions can be expected to achieve their objectives. So you're creating machines that are in the image of intelligent humans pursuing objectives that are in the machine. And of course, we have to put the objectives there. They don't come with objectives out of the box. And that is the standard model. And I've argued that that standard model is a mistake. So what are we going to do instead? Well, we really want machines to achieve our objectives. And so we want machines that are beneficial, meaning that their actions can be expected to achieve our objectives. So this is more difficult because our objectives are in us and not in them. But this is, in fact, I'm going to argue, what we want. This is a new model for artificial intelligence. And here's how it works. We call it Provably Beneficial AI, which is an aspirational term. The principles, of course, there are 3 of them. The first one says that what the AI system, or the robot, I'm going to call it, is supposed to do is to satisfy human preferences. And here, by preferences, I don't mean, pizza flavors. I mean what you want the whole future to be like, everything that you care about for as far into the future as you care. The second important point is that the robot does not know what those preferences are. And this is the crucial difference between the new model and the standard model. And it turns out this uncertainty about human preferences is what protects us and allows us to stay in control. The third principle basically connects robots to humans. It provides an information channel for information about preferences to flow from humans to robots. And that principle is that preferences are revealed by the behavioral choices that we make. They're revealed imperfectly, of course, and through a very complex cognitive process, and I'll talk more about that later. So these general principles are designed not for the robot to read and follow, but for human designers to know how to set up the formal problem that their algorithm is going to solve. So we call this formal problem an assistance game. It's a game because it contains multiple players, at least one robot and at least one human. And it's called assistance game because the robot participant is sort of constitutionally formulated to be of assistance to the human when it solves the game. So to solve the game, you find the equilibria, as Nash called them, the equilibria of the game. And when you look at the equilibria of these assistance games, they have the characteristics that we want. The machine will defer to human beings. It will ask permission before taking an action that changes part of the world that it's not sure that you like or dislike. Conversely, you can think of its actions as minimally invasive. So it changes only those parts of the world that it's sure you want changed. And most importantly, it will allow itself to be switched off. So this is the core safety problem for AI. And roughly speaking, the better the AI, the closer it comes to human level or even exceeding human level of intelligence. In this model, the better the outcome, because it's better able to learn about human preferences. It's better able to achieve those preferences. So let me talk a little bit about this idea that the machine will allow itself to be switched off. So in the standard model of AI, the one way this goes wrong is that we specify a goal, such as I must fetch the coffee. And then the robot thinks to itself, okay, I must fetch the coffee. I can't fetch the coffee if I'm dead. So just as a consequence of having the goal, the robot is thinking to itself, I have to preserve my own existence. This is not an instinct or a primal drive that we build into the robot by some sort of erroneous engineering design, but it's actually just a consequence of having a fixed objective. Now, once the robot realizes this, then it realizes that it has to disable the off switch. So this big red off switch on the back of the robot, it will figure out some way to disable that so that no one can switch it off and interfere with the mission of fetching the coffee. And it might take other extreme actions to protect itself preemptively against any possibility of failure. So this is what we want to avoid. Now, in the new model, the thought process is somewhat different. So the robot thinks to itself, okay, the human might switch me off, but only if I'm doing something wrong. Now, it doesn't know what wrong means because it doesn't understand our preferences, but it's going to allow the human to switch it off because it wants to prevent whatever it is that the human doesn't like about its behavior. So I know what wrong is, but I don't know what wrong is, but I know I don't want to do it. So I should let the human switch me off. And of course, this is a hand-wavy argument, but we can do what mathematicians always do, which is to write everything in Greek, and then we get a theorem that the robot has a positive incentive to allow itself to be switched off. And if you know the theorem of non-negative value of information, this is exactly isomorphic to that theorem. So there are lots of complications, as you can probably imagine. And probably the first one that's occurred to you is that there's more than one human. And certainly the diversity of human preferences is important to represent, and that's no problem. We can have billions of individual preference models, just as Facebook has. The key issue is how do you trade off the preferences of multiple individuals? How do you make decisions on behalf of the people, so to speak? And this is a question that's engaged philosophers and economists and political theorists for thousands of years. We don't, of course, have a better answer than they do. And there are still many open questions around the edges of this question, I might say. Another important point, as I mentioned earlier, is that the connection between human preferences and human behavior is not a straightforward one. It's not rational. We make mistakes. We're emotional, we're computationally limited, and so on. And so in order to reverse engineer or invert behavior to access the underlying preferences, we need to understand something about psychology and perhaps neuroscience as well. We have a lot of work to do to rebuild the foundations of AI, because after all, every chapter of the textbook is based on the assumption that we have a fixed known objective, whether it's a goal and a cost function as in search or reward function as in reinforcement learning. That assumption has to be relaxed. We need new problem formulations, new algorithms, new theorems, new technology to basically implement the new model. And then, of course, there are many applications. Self-driving cars come to mind, where the car should adapt to the preferences of the individual, not just for where they want to go, obviously, but how they like to be driven, and how long they like to wait, and all kinds of other aspects of their preferences for driving. And personal assistants, whether they're digital or physical, obviously will need to learn a lot about the preferences and activities of their owners, as well as respecting the preferences and activities of others. So if you're interested in learning more about these questions, there's a book, which is a non-technical book, published last year, called Human Compatible, or you can buy the 4th edition of the textbook, which has all the technical underpinnings that I've talked about scattered through the chapters, although still the bulk of the technical material follows the standard model. So to summarize, the standard model for AI has been successful with simple systems in the lab, but in the real world, it will lead to the loss of human control. If we take the new model, Provably Beneficial AI, that involves a coupled system of humans and machines, and analyzes that coupled system, sort of a co-design, if you like, but we really only get to design the machine half of this coupled system. And it's not only possible, but it's actually what we would really want, economically, as well as from the point of view of safety and control. Such systems will actually be desirable. People will prefer to have these rather than systems built in the standard model. There's a few obvious unsolved problems. The first one is why would Dr. Evil actually use these kinds of systems? So this is the misuse problem. The second problem is that we might overuse AI, that we might essentially turn over too much of the management of our civilization to AI, as happened in Wall-E. And basically, that's an irreversible process. So this is not just an AI problem, but it's a very important cultural problem that we haven't really addressed yet. So with that, I will say thank you very much. And we're happy to take questions.
Thank you very much, Stuart. That was a great presentation. I can tell from the Q&A online, it's really perked quite a bit of interest for everybody. And just double checking with our team, Stuart certainly can be in the frame as well at the moment. So bear with us as we continue to work through the optimal method of projecting everybody's images in this video. I do have some questions that have been coming in, and the first question, Stuart, that I'd like to ask you. You talked about objectives, right? You talked about picking good objectives. So regarding that process of picking good objectives that are beneficial for us, how might we build systems that in some ways increase our mindfulness and trust in what is actually beneficial for us, especially in a world where our influences and information are increasingly managed by AI? And of course, this has connections to the current pandemic on even basic questions like whether COVID is real, worse than the flu, et cetera. But I wonder if you could respond to that.
So yeah, great question. So I think we have to distinguish between what we might think of as short-term goals and our long-term preferences. So theoretically, at least, your long-term preferences shouldn't be affected by your beliefs, right? So you might believe that the COVID virus doesn't exist, that's fine, but that doesn't affect whether or not you want a future where you get sick or a future where you don't get sick, right? So The other point is that you may have short-term goals which you have derived by an inexact process. So you have some long-term preference. You say, well, that's my long-term preference. So in the near term, I should buy myself a Lamborghini. And that may be a mistake, right? So that may be far from the best way to satisfy your long-term goals about having a happy and fulfilling life. And so the AI system can advise you that, buy that Lamborghini might look really nice right now, but, by the time you've paid insurance on that thing for 5 years, you're going to be regretting that you made this decision. So this is something I think of it as bringing the future to the present. And this is something that AI actually can help us with. It's something that adults help children with. Well, you might not want to do your homework, but, do you want to spend the rest of your life flipping burgers? That's bringing the future to the present. And AI systems can help us do that.
Another question that came in, and thank you for that. Another question that came in was basically, how do we make objectives transparent, fair, and agreeable to everyone? Is it possible? I would like to stress again, we're not proposing to put objectives into machines. So that there's no notion that there's one objective and it has to be fair and transparent. The idea is actually that each person's preferences is what the machine is learning about. The question, which I mentioned towards the end, of how the machine is going to make trade-offs when it's making a decision that can affect multiple people, right? And I said that's something we've been struggling with for thousands of years. And the basic principle is everyone should be treated the same. Very roughly speaking, and there are axiomatic arguments going back to Hassani and others for this position, that you should make a decision that maximizes the sum of degree of satisfaction of preferences of the individuals. So let me just mention one of the philosophical caveats that people have. And this is Nozick's utility monster. So utility monster is someone whose range of affect is much, much, much larger than the range of affect of ordinary people. So something that an ordinary person, a raindrop lands on your head, okay, well, no big deal, right? But for the utility monster, that's an unbelievable catastrophe. And 2 raindrops is like 2 unbelievable catastrophes. So if that person's utility scale is much, much bigger than ordinary people's, then when the utilitarian AI is trying to make everybody happy, perhaps more attention, more resources will go to the utility monster. And so Nozick argues that, therefore, we shouldn't be making any of these allocation decisions. There should be no redistribution. There should be no trade-offs made whatsoever, which I think is completely untenable, right? A mother watching her child die from starvation over several months is more important than Jeff Bezos having to wait 1 nanosecond longer for his private jet to arrive. And I have nothing against Jeff Bezos, but I think he would agree with that, right? And some economists really believe that you literally cannot make trade-offs, that literally there is no way to say that one of those 2 things is worse or better than the other. And therefore, you can't make decisions that involve trade-offs. I just think that's nonsense. Very good. And maybe a couple more questions, because this is a fascinating discussion. I know my colleagues are going to be cringing because we're supposed to keep to a specific timeline, but hey, bear with me. This is a very good discussion, so let's take it a little further. Another question, along the same lines, we were talking about personal preferences, but how can you train AI systems to meet everyone's personal preferences across cultures? Are AI systems able to evaluate cultural attributes in the context of these personal preferences?
I would say yes, and actually this is something that goes on all the time already. For example, with multinational corporations, they learn models of what kinds of clothing or what kinds of food or what kinds of packaging, what kinds of product names make sense in each of their markets. Sometimes they make mistakes, but what you would hope is that this is what we call a hierarchical Bayesian model, right? There's a model for all humans, which covers the stuff that we all pretty much agree on. Like, we all want to be alive, we all want our children to be alive, we all want to be healthy rather than unhealthy, we all want to be safe rather than unsafe. So there's stuff which is true for almost everybody, and what that means is that when something comes out of the box, even if it comes out of the wrong box, like, even if you get the, Argentinian robot and accidentally ship it to Siberia, and somebody in Siberia unpacks the, the robot that was intended for Argentina, at least it gets that right. And then there'll be, subsidiary generalizations, like, typically all people of a certain age in a certain culture have preferences like this. And in the book, in Human Compatible, I talk about the member of the Green Party who lives in Berkeley, who just happens to eat whale meat and drive around in a Hummer, right? And so they would violate your expectations, but you'd quickly adapt to those peculiarities. But it would still be reasonable, once you found out that they were a Berkeley Green Party member, to expect that they would be vegetarians, even if that turns out to be violated. So the structure of the prior probability has all of these layers which correspond to all of the degrees of generalization and the scope of generalizations that would make sense for the full range of human cultures.
Well, very good, Dr. Russell. It's been indeed a pleasure. And on behalf of everybody on my team at Fujitsu, I want to thank you for joining us in this very, very great conversation. We've had a lot of interaction from the audience on Q&A. So thank you for joining us. And please do join us for the panel, which is coming up next. So without further ado, everybody, I'd like to move us now to our second panel of the day. The panel is entitled Accelerating Towards a Trusted Normal with Artificial Intelligence. And moderating the panel is going to be my friend Ajay Chander. And Dr. Ajay Chander serves as the Vice President of Research at Fujitsu's R&D lab in Silicon Valley. He has founded and led research across a variety of areas, including transparent AI, AI life assistance, digital healthcare and wellness, software tools, security, and computational behavior design. Ajay received his PhD from Stanford University, and his research has been recognized with several Best Paper awards, including the Most Influential Paper of the Decade, awarded by the Association for Computing Machinery. Congratulations. It's my pleasure now to welcome Ajay Chander.
Thank you very much, Dean, and welcome everyone to our exploration on accelerating towards a trusted normal with AI. We're delighted to have an esteemed panel of guests joining us today to share their experiences with the present and the promise of AI in the fields of science, education, and well-being. Dr. Daniela Ushizima leads machine vision teams at Lawrence Berkeley National Lab. Professor Victor Lee serves on the faculty of the Graduate School of Education at Stanford University. Russ Glass leads Ginger, an on-demand mental health company, as its CEO. As we look forward to hearing from our panelists in a few minutes, let's connect the theme of this panel to the events of this year and look ahead to what's to come. Our present pandemic has laid bare how much our lives, and indeed civilization itself, depends on functional networks. COVID has dealt a flow and capacity shock to human networks at all scales, from families to nations. This has impacted our individual and collective capacities. In response to the flow shock, we have rapidly transformed social interfaces globally, leading to large-scale experiments in new ways of working, learning, connecting as we are doing now, staying well, and living in general. And in concert, our systems of health and well-being, education, science, communication, and many others are reorganizing to deliver services across these new interfaces. All this disruption and reorganization has created a broad demand for trusted AI to enable collaboration and connection between people and information. By sparking collaboration and connection between people and information, such AI will serve as a trusted partner to our human networks, accelerate innovation, and assist the emergent social reorganizations that put us on a sustainable pathway to prosperity. To realize AI as a true partner to our human and social intelligence, we have some important problems to solve. For example, we need AI systems that are accessible and interactive, systems that supplement their recommendations with explanations, self-monitor to maintain a high level of durability as their input data sets change, are resilient to data deception attacks, and are designed with ethical frameworks in mind. And when we design AI systems in this manner, we will be able to more easily and more broadly integrate digital intelligence into our lives in a positive manner. Fujitsu Labs has a rich portfolio of projects to help realize this future. Let's sample some of them briefly. For example, towards making AI explainable, a need that is increasingly supported by international regulation, we have built new learning mechanisms that learn natively on graph data and separately on small data, while providing explanations to support their decisions. Additionally, we've built new mechanisms that aggregate high-quality knowledge from trusted sources at scale into knowledge graphs that can then be used for a variety of applications. One example is Deep Tensor, a deep learning technology that learns natively on graphs, learning efficient tensor representations of relationships that are then used to make predictions. And graphs are everywhere, so Deep Tensor is being used actively to partner with human experts in medical research, financial decision-making, and other domains. And this question of partnership between us and AI is a key one for the field. And as we heard in the keynote, it presents rich fundamental research questions for the future while we continue to make progress in the present. For example, we can represent the knowledge that comes through science, experimentation, our experience in digitally accessible ways, for example, as a knowledge graph. AI is a powerful partner in creating knowledge graphs at scale, from natural language processing to inferring semantic relationships between entities. And such growing intelligence assets assist continued human discovery and experimentation. This example integrates those innovations into a project with high social purpose. A national project for the Japan Agency for Medical Research and Development, we built AI systems to represent the medical knowledge inherent in a large number of academic articles and knowledge databases into a reusable knowledge graph. A combination of deep tensor and knowledge graphs allowed the AI to be a trusted partner for a human expert who is searching for solutions to a particular disease. Deep Tensor provides the graph-based recommendation, and the knowledge graph provides the explainability that enables the human expert to accept or to edit the recommendation. All of this accelerates innovation. And as AI accelerates social transformation, Fujitsu has made public its commitments to build and use AI in ways that enhance social trust and promote sustainability. We collaborate with various international bodies in this pursuit. And with that, we're excited to hear from our panel. As you listen to each of the panelists, please send in your questions at any time using the Q&A window on your screen. The second half of our panel will feature a discussion, and we would love to include your questions and curiosities. I'm delighted to introduce our first panelist. Dr. Dani Ushizima leads machine vision teams at the famed Lawrence Berkeley National Lab, with the goal of accelerating scientific discovery in the material sciences and in healthcare, amongst other things. She's also affiliated with the Berkeley Institute for Data Science at the University of California, Berkeley, and with the University of California in San Francisco. Dani, we're delighted to have you. Please go ahead.
Great. Thank you, Ajay, for hosting this panel. Good day, everyone. It's a pleasure to be with you today. I'm Dani Ushizima, and Ajay asked me to talk about my work on AI applied to images at the labs. And I was really honored and humbled. And soon after what you do, you ask for artificial intelligence. I actually use natural intelligence. I called my dad, who is a Japanese immigrant, a photo aficionado, and said, Dad, the VP of research, Ajay, from Fujitsu Labs of America, invited me to give a talk. And my father answered, well, if it helps, you can use my pictures. To what I said, well, Dad, it gotta be great. Because, it's Fujitsu. It's this leading information and communication technology company. To have my dad continue with his old photos. And I said, Dad, that's not what I do. I work with the new photos. These are science pictures acquired with very advanced equipment at Berkeley Lab, which, by the way, I'm showing here in this picture. Let's get a closer look to Berkeley Lab, or Lawrence Berkeley National Laboratory, which is one of the national laboratories maintained by the Department of Energy. And also Berkeley Lab has hosted several Nobel laureates. And some of the questions that they ask, science questions, have a lot to do with images. They range from tiny things like an atom to the universe, using microscopes to telescopes, and so on. So how AI is used here, it's basically to plow through these several images. So lots of the scientists use AI to understand the content of the pictures. This is about pictures. So let me start. Looking back at 100 years of photos, it's undeniable that pictures are important to record history. And my dad would say, well, in 1911, a Japanese boy that left Japan, left in a boat toward America to be a big success. And he went on and on, try to prove to me that photos are important documents, that photos serve as evidences of prosperity. Well, I couldn't deny. But also in science, pictures can offer key evidences in the process of understanding science experiments. And one of the simple things that we need to do in some of the pictures of science experiments is to count. Count not only people, but count cells. The difference is that Berkeley Lab uses more advanced cameras than those used by my grandpa in 1960, who I highlight here in this picture. He was the son of the boy that left Japan a century ago. Lots of things changed in 100 years. Image systems have evolved a lot during pests, during wars, even surviving an atomic bomb and the Manhattan Project research, which actually started by a Berkeley professor. Here's a picture of Berkeley Lab then. Berkeley Lab also changed a lot. After years of scientific research, the motto now for Berkeley Lab is bringing science solutions to the world, help the world, enough wars. And under that spirit, here's my work, is to create computer vision tools to help different kind of photographers. The photographers that I work with use a particle accelerator. And folks, it's fantastic. It's like having Superman's vision. You can see through things. You can see inside materials, particularly using one of these X-ray beamlines, the XRT, which is tomography, so that we can capture structural information from nano to millimeter, 2D, 3D pictures, and beyond. By using AI, we can explore pictures of today to deploy the materials of tomorrow. Scientific images are input to artificial intelligence computation to answer, for example, a simple question. Can I use this new material, ceramic matrix composites, or CMC, to build better aircrafts, lighter, more resistant airplanes, particularly turbines using CMC? In a collaboration with NASA, one of the questions that we're trying to help them to solve is, can we come up with better insulation to rockets so they can withstand very high temperatures with these carbon textile wrappings? And even in civil engineering, we've been working on understanding archaeological samples and unveiled the secrets of Roman concrete to come up with the modern concrete that will be self-healing, or green concrete. And you might ask, well, these are material science applications. The AI here, just to give you some examples of deep learning algorithms, we use convolutional neural networks to do semantic segmentation so that we can measure a microstructure of these materials. And it goes beyond. Moreover, we've been translating some of these applications to biomedical applications. So from material science to biomedical imaging. And yes, I do believe AI can be good. We can use AI to understand the dynamics of breast cancer cells, counting of the cervical cells, analysis of brain tissue in Alzheimer's disease. Specifically for cervical cancer cells, we are very close to deploying telemedicine applications. Another application of AI that we've been working on is on classification problems. And here, what we're doing is something similarly to Pinboard in Pinterest. But instead of looking for lamps and cushions, imagine if we could find instead, using this whole machinery, this inference to find bed cells or cancer cells. So that's a little bit of what we've been doing at Berkeley Lab. Thank you so much for your attention. I leave you in great company with the other panelists. Thank you, arigato gozaimasu. And just to say that these are my opinions. I've been funded by several agencies. Thank you so much for your attention.
Thank you very much, Danny, for bringing us on that journey with you, especially guided by images. That was wonderful. Let me now introduce our next panelist. I'm delighted to introduce him. Professor Victor Lee serves on the faculty of the Graduate School of Education at Stanford University. He's also the president of the International Society of the Learning Sciences. Through his research, he tries to understand the new opportunities for people of all ages to learn STEM content and practices with the support of emerging digital technologies. Victor, delighted to have you. Please go ahead. Victor, we can't hear you, just in case you're still on mute.
Is that better?
Yes, loud and clear.
Okay. Thank you. I apologize for that. There's an important question that people working in education have to ask early on when they begin that work, and it's, what should learning look like? Now, for technology enthusiasts, one place where we can look is in science fiction. Science fiction, beyond being entertaining, can serve as a window into a possible future. But beyond being a window, it's also a mirror on our aspirations and our fears and our biases. I have on this slide here images of what education might look like in the world of Star Trek. Take a look. What do we see? In one version, we see a young Spock on the planet Vulcan. He is in a learner pod that adapts and is personalized to him. At the moment, he appears to be doing something that looks like calculus. The system moves quickly. It provides new information just in time that is customized just for him. And if you look on the picture on the left, there are other pods in the distance where presumably other Vulcan children are experiencing their own customized and personalized learning environments. Right now, we have people developing AI for education that can do this, adapt and personalize learning experiences for each individual student, and carve up fields and disciplines into chunks that are just right for a scheduled learning episode. But I also ask, looking at those pods, doesn't that seem lonely? So you can look at the picture on the bottom right, and that's another Star Trek image. That's the class or students on Deep Space Nine. And what do we see there? Well, we see computers for every child and the teacher. And I think this is encouraging that there is a human teacher there, because one of the mistakes that we can make in thinking about future technologies and future AI or education is to think that the technology replaces the teacher. It doesn't. It can't. Instead of thinking of AI as a replacement for teachers, we're going to get a lot more mileage out of thinking of AI as a partner or recommendation tool to help teachers. It can take on some of the more tedious activity and point out some of the patterns that the teachers may not notice in the moment of their teaching, and leave it up to the teacher to decide how best to proceed. that would be a sensible AI for teaching, where we trust the expertise of teachers who know their students and know what interests them and what experiences they bring to the classroom. One thing that a lot of people came to appreciate during the COVID-19 pandemic is the hard work that teachers do. So AI could make that work a little bit easier. Another thing that we learned during the COVID-19 pandemic is what we miss and value about school. One of the things is that school is social. Learning is a social activity, and we can get so caught up in the idea of personalization and individualization that we don't think about the many other configurations that kids are in when they're learning. We miss having our kids learning with other kids. That social aspect is something we need to design for in future AI for education. So imagine that future AI can help monitor how a group is working together and offer suggestions on how they can work better. Imagine AI that can pair students together who can benefit most from working with one another because each kid knows something that the other doesn't. We need a future education that helps kids learn to work better with each other and to work with well-structured problems, not just solve calculus equations. Also, looking at these pictures, notice that learning is embodied. AI work in education gets so caught up in digital information that we're missing the opportunity to make inferences from inputs that aren't keyboard strokes or button presses or screen taps. We need AI that can help figure out what's going on in a classroom or a learning space, who's participating, where in the room is the teacher needed the most. AI should sense what's happening in the room and provide useful feedback about how students are engaging and offer ideas about what can be done differently the next day and the next after that. And you know what else? Learning isn't all work. It can be fun and joyful. If you ask me, I would like more of it to be fun and joyful. We need AI that supports that lets kids wonder about the world and not wonder if they got a certain math problem right, or if the AI behind their system thinks that they got the math problem right. We need AI that can respond to and appreciate a bit of humor and a little bit of childish subversion, just like how voice assistants now have fun Easter eggs, and we can program them as end users to say silly things for the sheer joy of it. Historically, education has had a mixed relationship with technology, and that's going to apply also to AI. One of the problems is a matter of trust. Teachers, educators, schools regularly encounter situations where the use cases of the technology don't match the real-world needs of a given classroom. Right now, AI struggles with the long tail of unexpected situations that come up in a typical classroom. And that's why teachers are important. They make the quick judgments on how to deal with those in ways that are sensitive to the students and to the situation. And AI needs to be a trustworthy assistant. AI needs to be humble and make useful suggestions at the right time and in the right way so that it's something that feels helpful and not intrusive. It needs to be accountable to how learning really happens in its social and embodied forms. And for any techniques that rely on student data, as parents, we know that there are going to be a lot of sensitivities to consider with respect to how private those data are and how they're being used. So my parting message is that if we want to think about how we build trust in AI in the future of education, then those of us who are involved in the design and development world will need to start from a position where they themselves trust what happens in the classroom as being important and worthwhile, and that teachers should have a lot of say in how to deal with situations as they arise.
Thank you so much, Victor, especially on taking us on the back from the future journey and grounding us in some open questions that we have to address as a community. I am delighted to introduce our next panelist, Russell Glass. Russ Glass leads Ginger as its CEO. Ginger is an on-demand mental health company recognized by the World Economic Forum as a technology pioneer and by Fast Company as one of the most innovative companies in healthcare. Russ, we're delighted to have you. Please go ahead.
Thanks, Ajay. and thanks for having me. It's great to be here. It's been a super interesting session so far. And I was asked to talk about use of AI and machine learning in healthcare. Ginger is a pioneer in this space, and we're doing quite a bit really to solve a very specific problem, which is that there is a huge supply-demand imbalance in the mental health space. There are far more people who need care than can get access to care. And when you look at those curves, the fact that millions of people have a mental health disorder but can't get access to care, they're actually diverging. And this was even pre-pandemic, where far more people were presenting with anxiety, depression, suicidality, but fewer and fewer providers were going into the mental health space. So we see this divergence, and we recognize that we weren't going to be able to solve this problem with traditional methodologies. There weren't enough people going into the space. There weren't large enough networks to solve the problem that humanity has in mental health. And yet the cost to society is staggering. The World Health Organization estimates that it costs us about $1 trillion a year. When you combine the healthcare costs going up, the absenteeism in workplaces, the presenteeism in workplaces. And so we looked at that and said, okay, we need to be able to innovate and create a new way of delivering care. What technologies can we use to deliver more effective care and provide access to things like behavioral health coaching, things like therapy, things like psychiatry in a much more efficient, yet still high quality and effective manner? And so the system that Ginger built combines real care, real people, with virtual delivery, things like chat-based care, things like video-based care, and it brings AI to the table to accomplish a number of different activities. And so I wanted to talk a little bit about how we're using it today and where I think this is likely going over time. We use AI specifically today to do 3 core activities to help us scale our platform. First is decision support. Second is quality assurance. And third, and probably what people get most excited about when they think of AI, is automation. But interestingly, starting with decision support, this is probably the most important thing we use AI for today. And it allows our care teams to provide far more care at far higher quality because they have a teammate in AI helping them make good decisions and helping them create more personalized care. So as an example, when somebody comes in and we start to do a intake, we're using natural language processing to extract features from that intake. We'll understand their background, their history. We'll understand medications or prescriptions they have, maybe family history. We'll understand tone of voice, how they're talking about their condition. Based on all of this data, real time, as our coaches are interacting with them, they're getting recommendations on what is the next best action they could take for this member to both personalize the care pathway and make sure they get healthy as fast as possible. They're getting recommendations on suicidality. Is this person showing a high level of suicidality? They're getting recommendations on escalation requirements. Should they escalate to a higher level of care, let's say to a therapist who's licensed to provide things like dialectic behavioral therapy or cognitive behavioral therapy, or even to a psychiatrist who might prescribe medications for this person's condition. So that decision support allows us to provide far more care than we could provide otherwise. Our coaches have panel sizes of about 400 plus active members today. So think about that for a second, that a single coach can handle this many people. They wouldn't be able to do that without the decision support that the system provides. The second thing we use it for today is what we call quality assurance. So how do we make sure that our coaches are high quality, that they are providing the right levels of care, and that people are getting healthy? It would be super expensive and time consuming to hand check every single transcript or every single interaction. So we use AI to do that, where we're looking and monitoring these chats. We're making predictions about where these conversations should be going. If we see anything anomalous, let's say somebody's not getting healthy as fast as we'd expect them to. Let's say that the coach is making a decision that we wouldn't have expected. We then kick it out automatically to review by a clinical oversight team. So we're doing a manual review. We're looking at, did the coach make a mistake? Is the algorithm off? The coach did a good job, but the algo got it wrong. And we'll make changes to the system, either training the coaches better or changing the algorithm to be better tuned to understand what happened here. The third big area then, again, that I think a lot of people think about when they think of AI in healthcare is automation. And we're automating the experience in a number of ways today with a continual goal of supply-demand imbalance. So how do we continue to deliver more care per unit of supply? Today, we're doing things like note summarization. So when a therapist or a coach goes through a session, instead of spending 20 minutes having to type up those notes, we're doing that for them. When they are interacting with one of our members, we're pushing recommended replies right into their, what we call their portal, so that they don't even have to type the reply. They can just use the recommendation of the system, but with one click and reply to the member. They still have the ability to edit that response or ignore it. So it's still coach driven, it's still clinician driven, but they have the ability to speed up response through our recommendations. We're currently working on Smart Complete. So similar to what you might experience in Gmail or Microsoft Word today, you're typing and it's predicting what you're going to complete that sentence with. We're doing the same thing, but for clinical reasons and clinical purposes. Over time, as confidence intervals go up, we will start to be able to talk directly to end members with automation. So today we're using it. The coaches are making decisions. The clinicians, they might edit it for tone. The coach might change it for tone. They might ignore it altogether. All of that signal goes into our algorithms, allows us to get smarter and smarter over time. And again, ultimately, we think there's a day where we could have entirely automated psychiatrists prescribing medication, providing emotional response to help us solve the supply-demand imbalance. So Ginger is, we're huge fans of what's possible here, and we hope that we'll be able to bring one of these AIs to you in the near future. Thank you.
Thank you very much, Russ. Mental health, as you said, faces a very unique supply-demand imbalance, and I think is a fantastic field in which the potential of AI to truly augment the capacity of an individual person to provide other care is augmented in order of magnitude. So with that, let me invite all of our panelists to turn on their video and mic so that we can get into some Q&A and discussion. And let me just say at the outset that I find all of these fields fascinating. I find all of the work you're doing fascinating. I could speak with you, all of you individually, for an hour each, but we have 20 minutes. And there are so many fantastic questions, both individually in all of your fields and also the intersection of some of them. So let me just start with the one we were just talking about in mental health, because we're sort of doing a contemplation on trust today, and particularly in this session, especially as we place to be a partner to us in teams and individually. And one question that shows up is about how different people conceptualize trust. A parent may look at it differently when that parent is trusting a machine to augment a learning program. And a patient may look at it, and a physician may look at it differently when they are doing it for care and so on, for scientists and so on and so forth. So one question that I would have is how do you conceptualize trust when it comes to using AI in your field? And how do you assess it now? And if the tools are not quite sufficient, what might you look for from the research community in terms of assessing trust in your domain? And Russ, maybe let's just start with you, because we've sort of had some context from you just now.
Sure. Well, the first thing is we spend a lot of effort thinking about that human interaction with our technologies, and ultimately, as we start thinking more and more about the experience of interacting with an AI, we've really come to the conclusion that AI needs to feel like it's part of a team, that it's not a standalone experience, but it's another team member. So you might have a coach, you might have a therapist, you might have a psychiatrist, and you have this AI that are all working collaboratively on your behalf. So that's number one, is the feeling that you can create that this is a team, so that you can build trust by watching how this team interacts for your benefit. Two is we see it being critically important that we're transparent in this is automation, and explaining what this is and what this isn't to the end user. Introducing this as an automation to somebody who's in the middle of care and has never seen anything like this is probably not going to be a very well-received experience, or it's more difficult to create an experience that they're going to trust. But if you can introduce it up front, and introduce it in a way where that AI is explaining, hey, I'm so-and-so, I'm an AI, I'm going to be your guide and teammate when it comes to getting care from Ginger. I'm also going to introduce you to your coach, to your therapist, and your psychiatrist if medication management's needed. And I'll be there if you have any questions for me. This is the kind of interplay that I think will be actually not only not scary to people, but well received, because that feeling of being surrounded with care and having something that's always available to them is, I think, a very positive one.
So one of the things that happens when we separate capabilities into transparent, distinct entities is that the receiver makes different mental models of them. So I might have a mental model of public health professionals. I may have a mental model of politicians. I may have a mental model of a parent, of a teacher. So Victor, sort of pulling on this question of interacting with AIs as we go into an AI-richer world in all domains, I'm curious how you think about what have you observed is changing in the mental models of learners as they incorporate entities like Alexa's? Certainly over the last decade, we've seen entities like Wikipedia become first-order, distinct information sources accessible to everybody. But the new class of entities not just answers a question, but it has the ability to do proactive things. And in your words, not quite embodied learning yet, although with robots that's also being experimented on, as you know, but certainly is on the edge of doing social learning. So just generally, we'd love to hear your thoughts on the interplay between trust, the mental model a learner might have of an AI in their teaching team or support team, and any thoughts on that?
Yeah, I'd be happy to comment on that. Currently, we're seeing a lot of youth experiencing AI as a tool that's always been around. So they expect quick and ready information, and for the AI to provide that. I think that's changing the kinds of problems that they think are going to be relevant to encounter in school and the kinds of problems that they'll solve, because they feel like they can just ask Alexa, just look something up, or just follow some information trail to get to it. So I think their expectations for the kinds of things that one would do that's enjoyable and worthwhile in their education and in their schooling is going to be widened because they're counting on and expecting the AI to have ready access for all the information that they're needing and wanting. Right now, because there's enough bugs in the system, they find a lot of the mistakes funny that AI makes. And so I think that's actually been a good offshoot of that humor part of it. But I think as we come to rely on it in higher stakes situations outside of the classroom, the expectations for AI to be more trustworthy are going to go up.
That's a really good point about how children perceive the AI, the humor in AI, or perceive humor in the fallibilities of AI and sort of work around it, and sort of it's part of how their mental model and expectations for it are more natively and differently being developed than perhaps ours. And Danny, when Victor was speaking, I was thinking back to your talk about showing us a palette of images that a machine learning model helps a scientist more quickly search amongst perhaps make more better hypotheses faster. And just connecting, your two domains, education and science, I was just wondering, Danny, like, how would you train a 5-year-old scientist today or a 10-year-old scientist today? Because it is possible that this particular scientist may have available to her or him natively a pattern matching tool, right? And a 5-year-old might be given such a pattern matching tool to find the right fairy wings or the right Lego parts for building a autonomous machine or a real fairy that has magical properties, because the AI components have those properties of vision and actuation and so on and so forth. But if you were to sort of, this perhaps is a question of the intersection of both education and science, how would you take what's possible in AI in 2020 and what is going to be possible in 2022 and 2025 to train a scientist of today, any ages between 5 and 25?
So you mentioned recommendation systems. I think there is a huge potential, but I'll quote my friend Victor Lee, the AI needs to be humble. And I think that's what's missing a lot these days to understand what's actually AI capable of doing. In recommendation systems, I mean, it can be a very useful tool, but depending on the models that you create, how simple they are, they might actually look for correlations that actually don't mean exactly what you're looking for. And a simple example was this picture of a dog in which, it was the dog. Well, I'm sure this particular kind of dog, but there was something in the background of some of these dogs that was a correlation with an element in the background as opposed to the object of interest. So these are funny things that happen to AI. And here, when the problem is dogs and cats, that's not much of a problem. But when we're talking about material science, in which you're going to deploy a material that it has defects or not, then it becomes more complicated, when that correlation might not indicate that that cell is really bad or not. That's a big problem. So moving forward, I think, we need to make AI more transparent. I do think we need to certainly be humble when looking into AI and finding better ways to explain. And I was really impressed with your presentation, by the way, Ajay, in which you show visualization as one of the mechanisms to really make AI more transparent. So in a sense, you're trying to enhance the domain scientist or your user. You're making a superhuman, if you will, as opposed to, I'll just substitute the human. The machine will do all the work.
And to add to that, I want to go from that notion of fairy wing recommendation engine, in that the AI, I want to go back to the point about things being fun and lively and a little bit subversive. I would love to see a system for young children which will take their drawing, make some sort of confused inference as to what it is, and create a funny or silly cartoon that they can play with. Sometimes the ambiguity or the lack of certainty or lack of clear ontology is a beneficial thing. That prompts conversations for learning to happen. So to just be really sensitive to the situation and opportunities to have fun with it and let the users have fun with what the AI is going to do.
Absolutely. This brings to mind something some painters say sometimes, that when they move to digital tools, what they miss is the accidents of paint that sort of spark new creative flourishes that would be useful sort of pre-program to bring back. So Victor, I wanted to ask you a little bit about, you talked about fun and joy, and I wrote down wonder about the world. And certainly one of the things we want kids to do, and quite honestly, everybody to have, is curiosity about the world, and pathways to fulfill that curiosity with trusted knowledge. From your perch as a education researcher and so on. What is your view as we look over the next decade regarding what should we educate children for, given the AI-richer world of 2030 and beyond?
Well, I think there's actually a very important need for kids and for the schooling system and standards to shift focus so that topics that are related to computation and AI and data science take center stage. It's not going to necessarily be that every child's going to graduate from high school ready to be a data scientist, but they'll be familiar enough that they can have good conversations and understand what's going on. And for instance, with this whole question of wondering and going to what Daniela was saying, was spurious correlations and letting them wonder, why did the AI do that? And what would I do to tweak that? Or what would I suggest people think about when they see those kinds of things and unexpected patterns are being detected?
So perhaps I'm going to use this in the future. Perhaps the lack of explainability of AI is a feature, at least in the context of engaging with little children, because it sort of boosts their curiosity. Well, before I go to the next question, let me put up a poll for our audience. We put up this poll for everyone in the audience. How would you like to use AI in the future? This is multiple choice. Choose as many as you like. Here are the choices: to find good answers to complex questions, to help discover good questions to ask, and to improve your personal or professional life. So we'll leave this up there as we continue our conversation. We have 6 more minutes. And let me bring in another question at the intersection of now mental health and education. I think if I have my statistics right, the American Psychological Association estimates that about half of mental illness starts by the age of 14, which, while a sobering statistic, is also sort of a call for action in intervening in the years where kids or human beings' attachment to technology of the day is pretty intense. And 3/4 of mental illness starts by the age of 24. So, I was thinking about school counselors, Russ, when you were talking about auto-summarization for, in the context of behavioral coaches for adults on your platform. If you were all collectively to think about a few years out in the future when we are looking at high school kids or middle school kids, where there is an intersection between all 3 of your themes. There's genuine education across all subjects. There's deeply heightened mental health needs because they are sort of getting rebooted as people after puberty. And there is the opportunity to really both spark and foster passion, whether it's for science or something else. How do you, in the model of AI being part of the school counseling team, the education team, the extracurricular team, I'd love to hear from each of you a vision of what life looks like 5 years down the line. Russ, perhaps we'll start with you.
Sure. I would say for the younger cohorts, so below, let's say, the ages of 13 or so, I think a lot more research has to be done on the effects of technology on the growing brain. I think there's some evidence to suggest that we have to be super careful about how much exposure to information the growing brain has, the lack of sleep being driven by devices being used too late at night. And so I think we have to be careful, frankly, about how much technology we're exposing children to until a certain age. I think as you then get into that 13 plus category where we know the brain is more able to handle more information and we see an opportunity to use technology very specifically to help call it adolescent populations with some of their mental health needs. I think it'll be a huge and growing area of attack because there is, when I talk about the supply-demand imbalance more broadly, it's even more acute in that age range. And to your point, that's where a lot of these issues start to crop up. And if you can catch it in a preventative way earlier, it makes it far easier to manage and hopefully stay out of acute care or anything more serious. So it's a critical area, and I think there'll be a lot more investment going into it in the coming years.
Let me move to the last question then for our panel to close it out. As a call for action to the research community, you all work in different domains. What foundational advances in AI might you like to see in the core tools that you work with to solve the problems that you see in your domain? So Danny, perhaps starting with you.
Yeah, I'm happy to. Well, certainly there are, technical improvements that are necessary that range from data representation and processing and prediction, better models, so on and so forth. But I think most and foremost, to be fair, and here are the FAIR principles of findability, accessibility, interoperability, and reusability. Certainly quality control. I think that was something discussed throughout the presentation. How we're going to make sure that these tools are doing what we're expecting, and is it what one person expects is the right thing? I mean, how we're going to evaluate this as a whole. How we do at Berkeley Lab has to do with including the domain scientists as part of the design of the artificial intelligence tools that we do. But I mean, lots of other AI tools are being used and not necessarily including a broader group of people in the decision process. Professor Russell also comment on the fact of ethics, and this has become a very hot topic within AI. I mean, what's actually ethical, right? If we're doing an automated system for deploying policemen, but we're all only surveilling a specific region, of course, we're only going to deploy to that particular region. And that's one of the topics discussed in a book that I recommend by Cathy O'Neill, Weapons of Math Destruction. So we certainly need to put more people on the table to discuss AI to come up with better AI.
Thank you. Victor, we'll give you the last word, please.
I think that there's this infrastructural matter that we'll need for education and AI to go hand in hand, and it's going to be dealing with data and privacy in a standardized way so people, parents, youth can specify how far will data get shared and what is the lifespan of some of those data. I think that's going to be essential for any advances to actually reach learners.
Well, thank you very much. We're at time, and here are some of the results from our audience. Something for us to ponder as we close. Thank you very much, Danny, Victor, and Russ, for joining us today, and most importantly, for your work every day.
Thank you.
Thank you. Back to you, Dean.
Thank you.